Meghna Bhatt, PhD student in the Department of Mathematics, extend a very warm welcome to you to this technical talk as a part of the talk series named TREES, which is Talks on Renewables, Empowering Earth and Sustainability by Global Center of Excellence in Affordable and Clean Energy, GCOE ACE at IIT Dharwad. This talk is on the occasion of an International Women's Day celebration at IIT Dharwad and co-hosted by the Indian Physics Association. I heartily welcome the guest speaker, Professor Sohini Kar-Narayan, Professor in the Department of Material Science and Metallurgy, University of Cambridge. I also welcome Professor Vandana Nanal, General Secretary of the Indian Physics Association. I now request our beloved director, Professor P. Seshu, to welcome the guest and the audience and to say a few words. Over to you, sir.
Thank you, Meghna ji. Good afternoon to everyone and good morning to Professor Sohini. First of all, let me wish a happy Women's Day to all the beautiful women in the audience here. I have found it to be a fitting occasion to have a leading scientist, woman scientist, deliver a scientific talk as a premier science and technology institute. This is a very apt way of celebrating Women's Day for us. I have myself heard some neurologists of repute say that women are not good in science. I think this is a fitting way to silence them, to showcase the women's power. We want more and more of you to be joining the STEM subjects, to be pursuing the STEM subjects through your careers. I think with the ministry's approach towards 20% target fixing for undergraduate students in IITs, our ratios, percentages of women students enrolling into STEM subjects has improved significantly. And I hope that it will continue to stay so and improve even further. On other fronts, I remember when I took charge in 2017, there are these inter-IIT events, and one of them is the inter-IIT sports events. And the students contingent from IIT Dharwad came to me for approval, as usual at the very last minute. Maybe they want to catch a flight tomorrow or something like that, today for approval. And then when I peered through the list, I immediately said, no, I will not approve this. And you can guess the reason. There was not a single girl student in the sports team from IIT Dharwad. I said, as long as I am the director, I am not sending a contingent from representing IIT Dharwad without girl students. So then and there, we resolved, we went to the girls' hostel. We brought in quite a few girls into the team, and then they went next day. But I felt very satisfied with the ending of the story the other day, when about 15-20 girls gathered me almost, saying that they want to plan for inter-IIT sports that is going to come in December. By the way, we are only in February, March now, to represent IIT Dharwad in basketball, in volleyball, and this and that. So it's really nice. I felt so happy to see so many girl students taking these sports, badminton, of course, and many others. So it is very gratifying that that little step that I took at that time helped to send the right message amongst all the students. And we are here celebrating International Women's Day today. Thank you, Professor Sohini, so much for readily accepting to come on board, give this lecture here. And thanks to Vandana ji and others in the Indian Physics Association for agreeing to co-host it with what we call as a 3G IITs, third generation IIT. We are among the 3G IITs also, probably we are the youngest because we have been inaugurated the last. But usually the youngest punches above its weight. So we have been doing pretty good over the last 5 years. We now have, I think, about 60 odd faculty members across various departments, maybe about 25 crores worth of sponsored projects, which comes to about 40-50 lakhs on an average per faculty member as sponsored research projects. We have done quite well in terms of industrial consultancy projects also. And our outreach program has been pretty good, which is actually housing this talk. We have this Center of Excellence on Affordable and Clean Energy. Using our Trimurti concept, we have the academia from IIT Dharwad and many other academic institutions that can later on become part of this. The industry sponsors, Honeywell is our sponsor. They have given us substantial grant this financial year and also promised that this Center of Excellence will continue to receive for more years to come. And we have an implementation partner at the grassroots level, which is the CELCO. It's an NGO founded by a distinguished alumnus and Magsaysay Award winner, Dr. Harish Hande, which will take care of implementation of these technologies in a pilot scale in a model village. We have identified a neighboring village, which we have adopted as a model clean energy village. So we call this as a Trimurti model. You have an industry, you have an academic institution which develops technologies, and you have an implementation partner, which is essentially an NGO, which has the grassroots connect. So under this Center of Excellence in Energy, it is appropriate that we are arranging Professor Sohini's talk. As all of you are eager to hear her, so am I. The nanotechnology efforts that she has taken in health have a lot of applications in energy and agriculture, biotechnology and whatnot. So while we will be listening to her work in health mostly probably, right, Sohini ji? Yeah, but we would be also looking at, as a young institution with several faculty members and researchers from across the departments, other applications also. And Sohini ji is truly inspiring for us because if I remember correctly, all her education has been in India. All her degrees have been from India, and she is a professor in Cambridge. So it shows what is possible if you are able to deliver at the frontier cutting edge technology level. So thank you for agreeing to give this talk, Professor Sohini. Welcome to you. Hand over back to Meghna ji, please.
Thank you so much, sir. I now invite Professor Vandana Nanal, who is also a senior professor at Tata Institute of Fundamental Research, Mumbai, to say a few words. Over to you, ma'am.
Yeah. Thank you, Meghna. Let me just share my screen. Yeah, you all can see my screen, right?
Yes.
Yeah. Thank you so much to IIT Dharwad and for co-hosting this lecture, especially on International Women's Day. And as your director, Professor Sheshu's opening remarks have set actually the tone for also the theme of this year's International Women's Day, which is Break the Bias. And I need not elaborate on that. You already have heard some things about it. So let me take a few minutes to tell you, acquaint you about Indian Physics Association. Some of you may be actually familiar with it. The Indian Physics Association was founded in 1970, almost 5 decades back. And as I was just remarking to some of the colleagues earlier, that the Dharwad chapter used to be one of the very active chapters. Today we have the presence in all social media, YouTube and the webpage. And if you need more information, please visit our webpage for the activities, and you can also write to either of these email addresses. So this is the, at a glance, IPS reach in the country. These are various chapters, or more than 40 chapters, and has about 4,400 members. The membership is directly available in the portal, and I'll tell you later. So what does IPA do? So it basically arranges several lectures it's the body which kind of provides a platform for the young interested students and teachers to learn about latest developments in the field. It liaises with other national bodies like Indian Science Academies, gives awards biennially to young scientists and senior scientists in acknowledging their contributions to the community, and has international linkages with other counter societies. It has an MOU with American Physical Society, Institute of Physics UK. Now we also have an MOU with Italian Physics Society, and is a member of AAPPS, that is Association of Asia Pacific Physical Societies. Last year, IPA organized joint webinars with APS, one on publishing with APS for the particularly aimed at students and PhD students, and one on the event aimed at towards gender equity, new directions and steps. This involved a panel discussion and two lectures by two eminent scientists. With IOP, we have an interactive lecture series program. So these happen alternatively once in India and once in UK. In India, these lectures are called Cockcroft-Walton lectures, and in UK, they are called Homi Baba lectures. This year, in both in 2020 and 2021, the program was online, and 2022 also will be online. This will happen in July, but this will be a special Cockcroft-Walton webinar focused on COVID-19 modeling, that is the statistical and impact of physics in COVID and impact of COVID on physics. Recently, IPA has endorsed the global effort on the role of physics in green economy, and I think it's more appropriate for this today's forum and the talk. So in addition to this, IPA brings out a quarterly bulletin called Physics News. This is also available now online, and there are special issues from time to time featuring scientists. Also, like for example, you can see here one with one issue based on S.N. Bose, his works, and where the current research interests are. Two special efforts are 2017, IPA brought out a special Physics News issue with all women authorship, showcasing the science done by women. Last year, we brought out an issue on Vibha Chowdhury, commemorative issue. Vibha Chowdhury was the first woman particle physicist in India, and this issue featured about her inspirational life story as well as the field cosmic ray research today. The Physics News features has a column called Meet the Physicist. We try to feature young and senior physicists telling you why do they like to do physics. So if you are interested in contributing to this or nominate somebody, please do send us a mail. And this takes, actually the spectrum is quite broad. We also feature a physics department in each issue, and I hope we can do a feature either on IIT Dharwad or in Karnataka University Dharwad. So current office bearers of the IPA are Professor Ramakrishnan, Director TIFR, he is a President. Professor Tanushree Sardas Gupta, Director S.N. Bose Institute, Kolkata, is a Vice President. Myself, Vandana Nanal, General Secretary. Professor Samik Mandal from Delhi University is a Joint Secretary, and Dr. Aradhana Srivastava is a Treasurer. IPA also established a Gender in Physics Working Group in 2017. This group is meant to provide a platform to address various issues related to gender parity in physics profession, particularly in India. In a unique effort, the GIPWG organized a very special conference of the physicists and the social scientists pressing for progress in 2019 in University of Hyderabad. The deliberations in this conference culminated into a Hyderabad Charter, which had several recommendations for the government's bodies and the institutions towards achieving the gender equity, providing career opportunities, and addressing various factors which actually are essential towards improving the work atmosphere and improving the ratio of gender diversity in the physics profession. Here I must mention, since it's appropriate for today's day, is that unlike many other countries in India, at entry level, there are quite a few women students, both in the school and high school. Even at PhD, though it is not very high, the numbers are at 20-25%. But the retention is very low. So as you go up in the ladder, the number of women scientists go down. So if you are interested in joining the IPA, please visit the webpage and then you can just log into our portal and have somebody, you can have a student membership, annual membership, or life membership. Any life member of IPA can actually propose another one. This is just a glimpse of some of the talks which we have heard last year. And IPA now runs an monthly colloquium series. We have colloquium on either first or second Saturday of the month at 5 p.m. All these talks are available on the YouTube. So as you can see, we have tried to span the subjects from the applications and the entrepreneurships to the pure sciences, and and also something as interesting as science experiments with a smartphone. This is something which is done by the Homi Bhabha Center of Science Education and has much wider thing. So let me now stop here and hand over back to the host. And I thank this speaker for agreeing to give this co-hosted IPA co-hosted talk, and look forward to an interesting talk. Thank you.
Thank you, ma'am. Now I request Professor Dheeraj Patil, faculty in charge, GCOE-ACE, to say a few words about the center.
Hello, good afternoon. Meghna, am I audible?
Yes, sir.
Yeah, so I'll share, I have a couple of slides to share about the center. Is the screen visible?
Yes.
Yeah. So this center is a global center of excellence for affordable and clean energy. This center is, as Professor Sheshu mentioned, center is jointly taken care by Selco Foundation with the PSA's office and Honeywell. So this center is committed to provide laboratory facilities, upscaling, research and development, as well as mentorship, then outreach and talks. The talk series that we have, this is the third talk that Professor Sohini is giving. This is called as a TREES talk series, which is talks in renewables, empowering Earth and sustainability. Then we have hackathons and challenges, innovation and incubation support in the areas of clean energy and affordable energy. As Professor Sheshu mentioned, we are having a grassroots implementation partner, Selco Foundation. So we have this field level experiences and this Trimurti that we have. So this is very much essential to try out what is been innovation done in the lab on the field. So currently we are establishing the lab equipments under various heads like testing and measurement equipment, as well as fabrication equipment, skill development equipment for scaling, and R&D in power electronics. As sir mentioned, we are having also the plan to have this field test lab, which we call as Model Clean Energy Village near to IIT Dharwad. The motivation for the center is the increasing environmental and climate change concerns, and the SDGs defined by United Nations, and these SDGs we need to achieve by 2030. So one of the SDG is SDG 7, which is affordable and clean energy, and targets are universal access to modern energy, increase a global percentage of renewable energy, double the improvement in energy efficiency, promote access to research, tech and investment in clean energy sector, and expand and upgrade energy services for developing countries. Also by 2017, we have to achieve net zero emissions. That is one of the target. So we are creating a fund to design and engineer affordable, energy efficient and renewable energy powered products to enhance the quality of life. So I urge you to go for contacting us, and our contact emails are also displayed here. That is office.ace@iitdh.ac.in and fic.ace@iitdh.ac.in. So thank you for this opportunity. Thank you, Professor Sohini, for agreeing for this talk. Thank you, and back to you, Meghna.
Thank you, sir. On behalf of the IIT Dharwad community, it's my pleasure to introduce the chief guest before inviting her to begin the talk. Professor Sohini Kar-Narayan is a professor of device and energy materials in the Department of Material Science at the University of Cambridge. She received her PhD in physics from the Indian Institute of Science, Bangalore in 2009. Following a postdoctoral appointment at the Department of Material Science in Cambridge, she was awarded a prestigious Royal Society Dorothy Hodgkin Fellowship in 2012 and a European Research Council starting grant in 2015. She was the recipient of a World Economic Forum Young Scientist Award in 2015 and was named as one of the top 50 women in engineering in 2021 by the Women's Engineering Society. Professor Kar-Narayan's research focuses on functional nanomaterials for applications in energy, sensing, and biomedicine. She is a co-founder and director of RTO Science Limited, a spin-out from the University of Cambridge that seeks to commercialize a novel, conformable, force-sensing technology for applications in orthopedic surgery, sports medicine, and beyond. Professor Sohini, we invite you to begin your talk. Please share your screen. We would like to inform the audience that you may post your questions using question and answer tab. Over to you, ma'am.
Thank you very much. Let me just share my screen. Yep, can you see that?
Yeah.
Okay, brilliant. Okay, good morning, or rather good afternoon to everyone on this call. First of all, I'd like to thank the organizers for inviting me to give this talk. I am really honored and very, very pleased to be here. So thanks very much to Professor Dheeraj for contacting me, to Professor Narasimha, and also Professor Saish for the really nice introduction. I'm really pleased to be here, and it's great to hear about all the wonderful things that IIT Dharwad are doing, particularly on this occasion of International Women's Day. I was really very pleased to hear that story you said about encouraging sports participation among women in your institute. As an undergraduate, I used to play basketball all the time. In fact, that's where you would normally find me if you were looking for me. At the Indian Institute of Science, I picked up badminton and other sports, athletics, whatnot, and I still play sports to this day. And I think it's very important to have that sort of well-rounded outlook. So yeah, work hard and play hard as well is my motto. So it's really wonderful to hear about all the great things that the institute is doing and all your. I really enjoyed hearing about this Trimurti model. It's fantastic. It really is. So yeah, so many congratulations to you for all your efforts. So coming to the subject of today's lecture, I'll dive straight in. So today I'm going to be talking about some of my group's work here in Cambridge on functional nanomaterials and devices for energy and sensing applications. And I'll try to explain all of these terms in the title as I go along. So to start with, I just wanted to acknowledge the people who are, who've done all the work that I'm about to present to you. So this is my research group, my students, my postdocs. I lead an interdisciplinary research group that works at the interface of material science, device engineering, and biomedicine. So here's a very recent picture of my fantastic group. This was actually the first time we were all able to meet in person in over 18 months due to COVID. So it was a really special day. The pandemic has, of course, brought about challenges and difficulties for everyone. We've thankfully managed to keep going. So I just wanted to acknowledge the people behind a lot of the science that you're going to see today. So with that, I just thought I'd first give you an overview about the work that we do in my group, and then I'll start to dive into specifics. So we work on developing a range of functional nanomaterials for functional devices. So what do I mean by functional nanomaterials? So by functional, I mean basically any material that is responsive. So it could be a material that, if you apply some pressure to it, there is a particular response, or maybe when you apply a temperature gradient, or any kind of physical stimulus that you apply to these materials, and there's a response. So when I say a response, perhaps there is an electrical response, or vice versa. You could apply, say, a voltage or a current to this material and cause it to do things. You could cause it to change shape, or you could cause it to get colder or hotter. So this is what I mean by functional. So these are responsive materials, and as you can imagine, these materials will find application in a range of different applications. So we use these materials to build up devices that do very specific, or that perform very specific functions. I hope that sort of sets the stage by what I mean. So when I say functional materials, I will be discussing today materials which are, for instance, piezoelectric. I'll explain what these are as we go along. Materials which are thermoelectric, materials which are electroactive, which respond to electric fields, to currents. I will introduce you to what are known as triboelectric materials. And some of the applications range from energy harvesting. In particular, in my group, we're interested in mechanical and thermal energy harvesting. These materials can find application in sensors, and a lot of the work that we're doing currently is geared towards biomedical applications, but also towards soft robotics, among others. Now, I also use the word nano, and you will see in a reason why in a minute why we're interested in this length scale. But for now, just remember that properties of materials at the nanoscale can differ significantly from the bulk. And so in my group, we also specialize in advanced nanoscale characterization techniques based on scanning probe microscopy. So these are advanced microscopic techniques that allow us to probe these functionalities at the nanoscale, because they can be very different at that length scale compared to the bulk. And so to go from these materials to devices, so how do we take these materials and make devices? We often employ additive manufacturing techniques, or you can think about these as printing techniques, whereby we start with an ink that contains the material that we're interested in, that has all that functionality, and then we print devices, layer by layer, to do a particular to perform a particular function. So what this allows us to do is it makes our devices flexible and stretchable, which I'll discuss in this presentation. And of late, we've also been using these techniques to introduce functionality directly into microfluidic devices. So these are devices where you've got these very small channels that direct fluid flow. Ordinarily, the channels themselves are quite passive. They don't actively take part in anything. They're just literally there to move liquids around. So what we've been able to do is, using these additive manufacturing techniques, we've introduced functionality within the channels so that the channel itself can take part in maybe in some sensing, for instance, of some bioanalyte within blood or sweat, etc. So all of this has been possible using this combination of functional materials and these very new and upcoming printing techniques. So just a word about print. Since we're on the subject of sustainability, manufacturing, of course, is a huge deal, and a lot of the manufacturing that we do is actually wasteful, where you start with something big and you kind of almost chisel it down to the shape that you want. So additive manufacturing flips this over, so you only deposit the amount of material that you need. So in that sense, you save on a lot of material. It's less wasteful, possibly cheaper as these technologies advance. So I'll touch on some of these different, these various aspects as we go along. But since energy and sustainability are the focus of this session, I will try to focus mainly on this. So my group has been interested in energy harvesting. So what is this? As the name suggests, it involves harnessing or scavenging energy from our surroundings and converting this into electricity that can be used to power devices. The energy being harvested would have otherwise gone to waste. So the ability to convert this sort of almost wasted energy into electricity is attractive on many fronts. Now, my group has been working in this field for a while, and so I'd like to motivate our research in this area as follows. So this is it. This is my motivational slide. We have all come across this symbol at some point in our lives. Basically, the symbol telling you that your battery is out of life, sometimes at the most inopportune moments. So it's very frustrating when this happens with our personal electronics like mobile phones or laptops. It means that you need to find a way to recharge the battery, or in some cases, replace it altogether. Now, extend this problem to all battery-operated devices that share the same issue. So many of these devices that I'm interested in are wireless sensors. And these sensors may be embedded within infrastructure like bridges for early fault detection, or they could be scattered far and wide across farmland to, say, monitor the moisture level in the soil. Or these sensors could even be implanted within the body to monitor vital parameters remotely. So you don't need to go to a hospital. You can, these sensors can read off physiological signals and send this remotely. And in this day and age of COVID, you can see why that would reduce the burden on healthcare. So the point is, how do we power these sensors without having to rely on traditional power sources like batteries that need to be replaced or recharged? Ideally, you would want some sort of a fit and forget device that could perhaps run itself without requiring intervention. And this is where energy harvesting comes to the rescue. So some of you might have already heard about this concept of the Internet of Things, which is basically this vast network of sensors that are meant to make our lives more seamless, more energy efficient, and less resource intensive. So when we talk about energy, when you think of the energy problems, there are two ways to look about it. So you could be thinking of ways of generating large amounts of energy to power cities and buildings and on that scale. So we're talking like megawatts, gigawatts even. The other scale is where we make more efficient use of the energy that is available to us. And it doesn't necessarily have to be just energy. It could be other resources like water, for instance. I mentioned farmland. So a lot of water is used in farmland, but sometimes you may not need to water as much as you're doing. So how can you tell when to stop and when to turn on the water just when you need it? So this is the example I gave about monitoring moisture level. So the only way we can do this is if we have sensors, right, which can tell us that, okay, now's the time that we need the water. Okay, stop right now, and we can save up on that. Or even electricity usage, like even in a building, a smart building that has sensors where you have the lights that come on only if someone is in the room. Or if you live in cold countries like the UK, a lot of energy goes into heating. But then there are buildings that are being heated where when there are no occupants even. So you need sensors that can monitor all of these things. And the more the number of sensors, and some of these could be for instance, I mentioned the example of bridges, say, or infrastructure or buildings, sensors that can monitor maybe a crack that has started to develop and can alert someone that there's something going wrong before the whole structure collapses. So these are called early fault detection systems. So that again helps us to make better use of the limited energy and resources that we have available. So these are just some of the examples. I'm just trying to motivate why these wireless sensors are so important, and they are starting to permeate our environment. But currently, most of these still run off batteries. And the problem is, if you've got acres and acres of farmland, who is going to go and replace all these batteries in the sensors in the soil every time they run out? So this is where energy harvesting comes into the picture. So where do we power? How do we power the Internet of Things? So we can look at the environment within which these sensors operate to find ambient energy sources, right? So these sensors can run off the energy that is available within the environment where they're operating. So I often ask my students, so what are some of these ambient energy sources you can think of? And straight away, the first answer I get is the sun. Of course, that's the sun with all the abundant clean energy it's an obvious place to start. But for many of these applications that I mentioned, so for instance, if you have sensors embedded in structures or sensors within the soil or sensors in your body, then the sun may not be the most convenient or accessible. And this is why in my group, we mainly focus on energy harvesting from mechanical or thermal energy sources, because you're never too far from something that moves or a temperature gradient in the environment. So this is primarily what I will focus on today, how we go from sort of these ambient mechanical energy sources or ambient thermal energy sources in the environment, how we tap into these energy sources and convert this into electrical energy, which is what we need to run our devices. So the way we go between mechanical to electrical energy is using what are known as piezoelectric or triboelectric materials. So these are those functional materials that I was telling you about. And I'll discuss some of this. And the way we go from thermal to electrical energy is using materials that are known as thermoelectric materials. And I'll talk about these in a bit. So let's start with mechanical energy harvesting. So again, just to remind you, I'm talking about wireless sensors, which typically require micro to milliwatts of powers. of power, which can be used in wearable or implantable devices or embedded in structures, etc. So again, we're not talking about gigawatts. We're talking about these tiny amounts of power. And you might think, well, actually, small amounts of power should be easier to get, but it turns out surprisingly not so, because as I mentioned, these still require batteries. But batteries have additional problems. But also these sensors are becoming quite small, but the batteries don't quite keep up in size. And you can see an example of this in your mobile devices. You've got your mobile phone. In some of these, almost a third of the weight is just the battery, right? So if we want to make these sensors smaller, less obtrusive, you want to sort of put them in places where you're not even aware that those sensors are there, then we need to make sure that the power sources are also sort of scaling in size. So looking at kind of mechanical energy, as I mentioned, you're never too far from something that moves. It could be movement from our bodies, we're constantly in motion. It could be movement from energy from moving machinery, flowing fluids. And the energy density in these types of vibrations is not very high, as you can see on the slides on the left. So nowhere close to what you could get from the sun, for example, but this type of energy is accessible, it's convenient, and under the right conditions, possibly enough to power these low power sensors. Piezoelectric materials in this context let me just find sorry, I just realized I don't have a laser point here. Here we are. So piezoelectric materials in this context can interconvert mechanical and electrical energy. So let's have a look at this. So the word piezo means squeeze, and a piezoelectric material, essentially the way to think about it is these materials, if you squeeze them, if you apply pressure, if you strain them, they produce electricity in response. So that's the functionality. And they do so by virtue of their crystal structure. So not all materials are piezoelectric. The ones that are have this property because of the way the atoms in that material are arranged. So it has to do with the crystal, with the inherent crystal structure of this material. And because of this, this particular kind of crystal structure, certain materials can produce a voltage when subjected to a stress or a strain. And it works the other way as well. So if you apply a voltage across them, you can cause them to deform. You can cause them to change shape. Typically, these materials are ceramic in nature, like barium titanate or lead zirconium titanate. But when you think of a mechanical energy harvester, so material where you keep applying pressure or you periodically strain the material to produce electricity. If you have a ceramic stiff material, then over time these they're mechanically unstable. They're prone to failure over this repeated strain cycling. So for vibrational energy harvesting or mechanical energy harvesting, these materials, although they produce a good amount of electricity for a given amount of strain, they're probably not the best from a mechanical robustness point of view. Piezoelectric polymers are a good alternative from the point of view of being flexible and robust, but they lag behind the ceramics in terms of their piezoelectric properties. So they're not as good. And part of the reason is because, as I said, piezoelectricity is rooted in the crystalline structure of the material, which is not always easy to control in polymers. So when you think of a polymer, you think of these long chains which are all kind of tangled up. So it's hard to control crystallinity in a system like that. And this is why materials which supposedly are piezoelectric, they do not have a large response. Although these would be perfect for vibrational energy harvesting because, as I said, they're quite flexible and they're robust, and they're actually a lot cheaper to produce than ceramics. So it's hard to control crystallinity of these materials unless, as we found, you work at the nanoscale. So this is where nano technology comes in, because at this length scale, you can control the crystallinity of the polymers quite literally because you're working with such limited quantities of the material. It's just easier to control using using materials processing steps. But importantly, it's not just the crystallinity, but you can also control their phase. So when I say the phase, what do I mean by that? So here's a very good example, just to give you an idea. So this particular polymer, it's called polyvinylidene fluoride. It's a very common piezoelectric polymer. It has quite a simple structure. So if you look here, it's got a carbon backbone, and on either side, you've got hydrogen and fluorine atoms on either side of the chain. And it can occur in what's called the alpha phase or the beta phase. And if you look closely, the difference here is that in the beta phase, you've got all the fluorine atoms lined up on one side, all the hydrogen atoms lined up on the other side, whereas in the alpha phase, they're sort of randomly distributed. The the point to take away from here is that between these two phases, only the beta phase gives rise to piezoelectricity, because there is what is known as a net polarization in this configuration. So basically, you've got these more electronegative fluorine atoms, and you've got these hydrogen atoms on the other side. So there's a net dipole moment going from sort of your more, almost think about it as also a negative charge center to a less negative charge center, and this gives rise to a dipole. You need this dipole you need this net polarization, as they call it, to have any piezoelectric properties in any material. So it's not that you don't have dipoles in this alpha phase, but as you can see, the direction of that dipole changes because these atoms are randomly aligned. And so the net polarization of this particular phase is 0. So someone might tell you, oh, PVDF is piezoelectric, but then if it's in the alpha phase, you can squeeze all you like, you're not going to get any electricity out of it. You need it to, well, for most of the material at least, to be in this so-called beta phase, where you have this persistent polarization. So in the bulk, typically, this is your thermodynamically stable phase. So this is, the alpha phase is what you would normally get, but we want the beta phase. And we want lots of the beta phase, because remember, these are semi-crystalline polymers. So even if you have some amount of this material, not all of it will be in one particular phase, but we want as much of it to be in that phase as possible. So we came up with a very simple method by which we could produce nanowires of this material. This is using a method called template wetting. It's been used for all sorts of materials to produce nanomaterials of metals, dielectrics, etc. So the idea is simple. You start with a nanoporous template. So think of it as filter paper with nano-sized pores, and you can infiltrate this filter paper. Of course, all the pores are the same size. And all of these are at the nanoscale. So you can infiltrate with some sort of a polymer solution or a melt. And after a controlled sort of heating, you get rid of any solvent, and then you can get rid of this sort of the top layer here, so that you're left with this template with all of these nanowires embedded. So this is after you've carried out a controlled solidification. So it's a simple, scalable, versatile technique. You can create all sorts of different shapes, all sorts of different dimensions just by changing the template. And you can also get rid of the template if you'd like to release these nanowires back into solution. So in the case of PVDF, for example, you can produce nanowires. So these are actually scanning electron microscope images looking at what these nanowires look like when you remove the template. And here's the interesting bit. So we usually use a technique called X-ray diffractometry to identify phases. And what you can see is that in just the bare PVDF powder, you have a mix of crystallinity. So you'll see alpha, beta, there are others as well, like gamma. And this is what we'd expect in bulk PVDF. Whereas in these nanowires, which is this red line here, we seem to have, managed to get this one beta phase that, which is what we want, because that's our piezoelectric phase. So it's quite easy to create a device out of this. So, where did we get to? We got to this point where we have our nanowires. If you put down some metallic electrodes, because if you want to produce electricity, you need to be able to collect this from your device. So we put down some metallic electrodes on either side of this device, and as you squeeze it, so the first experiments we've done was literally just tapping this tiny device, and they're very thin, these templates, because they're the nanowires are only about tens of microns long and about 100 to 200 nanometers in diameter. And as you tap, you produce electricity. So I'll show you it. It actually works. Let's see if I can. So let's see if I can get this to work. So here's a typical experimental setup that we built. So the device is actually sitting in between the oscillating arm and the rigid back. And you can see that this is how we generate current as the sample is being periodically vibrated. And then we have this circuit, which is basically a bank of capacitors that sort of charge up as we go. So don't blink now. We're going to discharge all of these capacitors in a second, and there you go. We were able to turn on an LED. So I know it doesn't seem like a lot, but this was our one of our first experiments where we had these polymer nanowires. We didn't push them through any they're quite easy to make as I described. And just by tapping on it, you can generate enough electricity, store it in some storage devices, and then use that to light up an LED. So it got us to the cover of this journal, which was great. And the fact that we had so much of this, the right crystalline phase, meant that, it was actually no surprise that we ended up with an energy conversion efficiency of 11%. So just to give you an idea of what that number means, if you compare to, say, a film of PVDF of the same material, you would get an energy conversion efficiency of 0.5%. So there's a massive jump. And the main reason for this is because when you grow polymers within a nano-confined geometry, you can end up with very good chain alignment. So it's not just a matter of having a lot of the beta phase, but also these chains need to line up so that when the overall polarization of the material changes, it happens across the entire device. So if you just had kind of nanowires all randomly aligned, then the individual polarization for each nanowire would just cancel out. So this is one of the advantages that this particular material had. So, just to say that we use this method to look at other piezoelectric polymers that have been reported in the literature, but which were mostly abandoned as their piezoelectric properties were quite poor. One such polymer family, which you'd have heard of, nylons. So certain kinds of nylons. So these are basically the polyamide family. Odd-numbered nylons in particular have a dipole moment in their structure, and remember it's prerequisite to have that for a material to be piezoelectric. But again, you have to get in the right phase and form in order to get these materials to be piezoelectric. We spent quite a while with nylon. I'm not going to go through the details of all of these, but just to say that we did a lot of work trying to understand how the crystal structure of these polymers, how dipolar alignment is affected in this material, and how we can manipulate this through processing. So for instance, here what we had basically done was to run some molecular simulations, playing around with different chain orientations, and we found that there's a so-called pole delta phase, which would give you the best piezoelectric performance. However, this pole delta phase is a metastable phase, so it's hard to come by in the bulk or even in films. And the only way to reliably produce this phase is through nano confinement, which is exactly what we did. Here are some images showing nylon nanowires on the left, and here is your typical device structure as I showed you previously. And as you impact this, as you sort of squeeze and release this device, you can produce an output voltage, an output current. You can try to measure the power output across a load resistance. So here we're varying the load resistance, and you can measure sort of the power that you can get out of these piezoelectric devices. The significance of nylon in particular is that you can actually get it up to quite high temperatures. So this is, we were able to run this up to 150 degrees, where a lot of polymers would just have melted by this point. So nylon is quite stable at high temperatures, which is what we reported in this work. So just to say that, understanding piezoelectric properties at the nanoscale is a requirement. We need to understand, what is giving rise to these piezoelectric properties, what these piezoelectric properties are. And because these are nanomaterials, we need nanoscale characterization techniques. And I mentioned this at the very start. So again, I won't go into too much detail here, but just to say, a very common method to measure nanoscale properties is using, scanning probe microscopy techniques. In particular, this is an atomic force microscope. I know some of you might have come across this. And it's basically a sharp tip on a cantilever. And as you sort of scan this tip across a surface, you can pick up sort of, features, microstructural features. So it's often used for topographic mapping, but you can be clever about this. So for instance, if you have a conducting tip, here's your sample. If you actually also apply a voltage across the sample, and if your sample is piezoelectric, so you can see that as you apply, say, an AC voltage, your sample will also deform at that same frequency. And using the optical detection that the AFM comes with, you can actually monitor the piezoelectric response. So this is just to give you an idea of how we actually measure these quantities. But mind you, these techniques are often not adapted, they work fine on films, or even hard materials. But when you have polymers which are quite soft, or nano or individual nanowires, a lot of times the tip can actually destroy the sample because it's a sharp tip and these are soft materials. So you might end up, destroying the sample, or you might end up causing the nanowire itself to move. So in my group, we spent quite a lot of time developing new techniques for non-destructive characterization. So in this case, rather than sort of scanning the tip across the sample and possibly destroying it, we actually tap the tip. And in that sort of, very tiny time frame where, the tip actually makes contact with the nanowire, this is where we do all of our sort of, piezoelectric response analysis. So a lot of high-speed data capture, data analysis that goes with this. I'm just putting this out here to give you, you will see quite a lot of nice devices that come out in the end, but I just wanted to give you a feel for sort of the groundwork that goes behind this, how we make these materials, how we optimize them, and how we measure them at this scale to really get to, what is it about our processing parameters that leads to higher piezoelectric performance or higher, functional performance in a material. So it's just important to understand what goes on sort of almost behind the scenes. So we have demonstrated this effect, using these nanowires grown in nano-confined geometries, how this can, how this improves piezoelectric properties in a variety of polymer systems. So I've discussed PVDF, I've discussed nylon. We've also done this for some materials which are biocompatible, for example, polylactic acid, and I'll come on to this a bit later on. We've also done it for some naturally occurring biomaterials which have piezoelectric properties. So, things like cellulose, collagen, even DNA, they have some piezoelectric properties. And so it's interesting to see what happens when you start to play around with these materials at these length scales. So quite a lot of work in this area. But while on the subject of polymers and mechanical energy harvesting, energy can be harvested even with non-piezoelectric polymers using an effect known as the triboelectric effect. And the idea is very simple. If you have two dissimilar materials and you rub them together, there can be charge transfer that takes place due to the different electron affinities, among other things. It's what we commonly known as static. So, if you comb your hair on a dry day, you find that it's starting to stand, or when you touch a doorknob and you get a bit of a shock. So it's that effect. That's called the triboelectric effect. And it happens, like we said, because you have two dissimilar materials which make contact with one another. So in a sense, we spend a lot of time trying to avoid static in our electronic devices, but in a sense, you're converting a mechanical motion into some sort of electric charge, which can be harvested. And so this technology kind of came into the scene, I would say maybe a decade ago. But of course, this effect has been known for more than 2,000 years. It has been documented, the static effect. So what has changed? Like, why did it take us 2,000 years to realize this? Well, what has changed is that we now have better techniques to engineer these materials so that you can have more charge transfer that takes place. Also, the devices that we wanted to power, remember I was talking about microwatts or milliwatts, the devices are requiring less power. So now it is actually possible to use some of these techniques to power these devices, which was not possible in the past. So, coming back to this triboelectric effect, like I said, you need two materials. Now, materials can be ranked in order of their tendency to donate electrons or to accept electrons. So some materials are happier to give up their electrons, some are happy to accept the electrons. So we call this a triboelectric series, and we have a sort of tribo-positive materials up here, tribo-negative materials down here. If you look at sort of the tribo-negative materials, these are materials that are happy to accept charge from other materials. A lot of these are synthetic polymers, which are great because it means I can make this in the lab. But if you look at the positive side, so ideally you want something that's high up in the positive end, something that's low down in the negative end, and you bring these together to have maximum charge transfer. But the ones high up here are often, things like skin, hair, so not materials that I can work easily with in the lab. Except you'll note that there's one exception, which is nylon, and I discussed this. This is something that we make in the lab, and what's very interesting is that we can, using these nano confinement techniques, we can actually push this nylon further up in the triboelectric series by making sure that it has a large surface charge density to begin with. Let me just show you a quick video just to give you an idea of how this works, because I think if you see it, it's always easier to visualize. So I'm just going to skip ahead. Okay. So here's a very simple triboelectric generator. So you can see that there are, so right here, there's a circuit that we're going to try to charge up. So there are a bunch of capacitors there, which are connected finally to an LED. So to start with, there's nothing, there's no charge in the capacitors. And now we've got a piece of Kapton that we're rubbing against two copper electrodes. And by doing this, we're actually moving charge back and forth, and we're collecting this in the circuit. And you can see that we can use this to light up our LEDs. There are other ways you could do this, so it doesn't have to be rubbing. It could just be sort of, a contact mode, what we call contact mode, where you make and break contact. So here are two materials again. We've got Kapton on one side, we've got copper on the other side. And what we're going to do is we're going to, in this case, we're not even going to go through a circuit. We're just going to connect the back of the Kapton. So there's an electrode at the back, and we're going to connect the copper directly to a bank of LEDs. And this is what happens. As you tap and release, you generate, a sporadic current, which can be used to, to power something. Of course, this is a massive device to power just a few LEDs, so maybe not very attractive. So the idea is we want to make this smaller, right? Because remember, size matters. And so this is where the concept of triboelectric nanogenerators comes about. So this is where, again, we manipulate the properties of matter at the nanoscale, such that we can do that same bank of LEDs, but this time you'll see the size of the device. It's tiny. That's it. So that device there is actually a template with nanowires, where the entire device, as you can see, is about the size of a 2p coin, and it's about as thick as your hair. So, that entire block, we were able to kind of diminish it to that tiny, tiny size. And the way we were able to do this is by playing around with the phase and the amount of surface charge on these materials. So here, let me just get my pointer back. Here we've looked at sort of the output. So here we're looking at the current output that comes out. So this is, when you have a device that you're sort of you're making and breaking contact with, where one of the materials is aluminium, which is sort of in the middle of the triboelectric series. Here are our nylon nanowires of a particular phase, delta phase. Here's another phase called the alpha phase. And you can see that if just by changing the phase of nylon, you can vastly improve the output performance. So here we're looking at power density as a function of the load resistance, and you can see that these alpha phase nanowires gives us the best performance. So this is just giving you, again, examples of how you can manipulate these polymers to get the best materials properties, which you can then use in various applications. Very recently, what we did was we fabricated what are known as triboelectric yarns, where you basically put down these polymer nanowires using a technique called electrospinning. So you can basically spin these fibers onto a conducting yarn core. So this is a carbon nanotube core. And the reason you need that, remember, you need some electrodes to collect the charge that you're generating. And again, these are just some SEM images showing you, that's your carbon nanotube core. So this is your conducting core, and these are the fibers that we've put around it. So this is a PVDF fiber, and you can end up with these sort of yarn-like structures. And the idea is that you can combine, so a tribo-negative yarn with a tribo-positive yarn. So, so we try to make a little weave here. It's not, it's not very impressive, but it's just to give you the idea that you can weave these materials together, for example, in clothing. And the idea is as you rub, as you, apply force, you can generate power, which is what you see here. And you can use this so here what we've done is we've used this to charge up various capacitors of various, of different capacitances in order to generate electricity. So this type, if you can sort of scale up the production and we can start to make these fibers, then in principle, you could wear these materials or wear these textiles rather, and generate electricity as you move around. So over the years, we've published quite a few review articles in the area of piezo and triboelectric polymers. So there's lots of fascinating material science and engineering. And if you're interested, these are all very good reference points. I'm going to change track here just a slight bit to show you another application of these functional materials. And because I know we have a mechanical engineering audience, I just thought you might find this interesting. So this is engineering materials, or engineering the mechanical properties of materials at the nanoscale. So what we've done is, again, we've used this template wetting method to create nanowires of PLLA. So PLLA is polyl lactic acid. It's a biocompatible polymer which the body is able to absorb and get rid of. And because these are piezoelectric, what we found is that if you can actually put down cells. So this purple, so this is a false colored SEM image. This purple bit here is actually a skin cell. So it's a dermal fibroblast. And when you put it onto these nanowires, which are these orange bits, so we're sort of looking from the top, you can see that these cells let out cellular projections and they grab onto these nanowires. So they're quite happy to be there. And when they grab on, they actually tug on these nanowires. These are piezoelectric nanowires. So if you strain them, you create, you can produce an electric charge, which we can sense externally. So the idea was to use these sort of piezoelectric nanowire devices as an interface for biological experiments, where you can detect the forces that these cells are applying as they clamp onto these nanowires. But at the same time, because they're piezoelectric, we can, from the outside, change the mechanical environment, because we can apply an electric field and then, get these nanowires to deflect. Why is this important? I mean, or, why is this so attractive? So the reason for this is that most cell biology experiments that are conducted on what is known as standard tissue culture plastic. And so you have these cells which kind of just sit there, and then you put in a bunch of different chemicals to see how they react, etc. There is no way to actually control the mechanical properties of this substrate. However, if you look at your human body, we have cells which have a huge range of stiffnesses. This is a log scale, right? So you've got softer brain or muscle cells, and then you've got bone at the other end. But the material on which you do these experiments would have like a very fixed stiffness. So what we want is a surface that is dynamically tunable. And in mechanical engineering, a simple way to change the effective stiffness is just change the aspect ratio of the surface onto which these cells might be sitting. So the idea is that you can lower the stiffness to more biologically relevant levels, because if you model these nanotubes via beam bending, then you can find that the stiffness of this surface decreases with the square of the aspect ratio. So basically, if you have sort of long and dangly, these will be softer. The effect, it's effectively softer. If you have short, stubby nanowires, then those would be stiffer. And by doing this, you can now start to, with the same material, you can start to span this entire range. And we've done some experiments with stem cells where you can put stem cells on different nanowire surfaces, and these stem cells respond to that inherent stiffness. So stem cells, if you put them on a soft substrate, they'll likely turn into a fat cell. If you put it on a hard, rigid surface, because of the mechanical environment, it might turn into a bone cell. And so now we have the ability to do this dynamically from the outside, because the other thing is you can tune the mechanical properties using electric fields. I just wanted to put that out there just to give you another example of how it's not just the materials, but using these nanoscale engineering methods, you can also play around with the geometry to get these new functionalities, as it were. So this is how we make these sort of soft piezoelectric interfaces where we can both sense and stimulate. So we're using these currently. We have a bunch of tests running with people who work with neural cells. We're trying to see if we can use our devices to create directed neural networks using this method. And at this point, I'm just going to switch gears a little bit, because at the start I said, we make all of these materials and then we fabricate devices. And a lot of the times we use what is known as these additive manufacturing, or rather microscale additive manufacturing techniques. So the goal here is to add functionality using these printing techniques. So we develop inks based on functional materials, and we quite literally print them in various combinations to make devices. And as an example, I will pick on thermoelectric generators. So these are, I mentioned at the start, so these are materials, or rather devices, which can, if you subject this material to a temperature gradient, then there's an electric current that flows, which is sort of what you see here. So if you have a device, so here there are actually two different thermoelectric materials, a P-type and an N-type semiconductor. And if you have a hot end on one side, a cold end on one side, it actually drives the flow of electrons through an external circuit. So you can have a current flow, so essentially it's a way of going between heat to electricity. And again, there's lots and lots of different sources of heat in the environment, and the electricity that we are interested in generating is geared towards these wireless sensor, small power applications. Now, as in the case of the piezoelectric materials, a lot of the conventional thermoelectric materials, the ones that people have studied over the years, are inorganic semiconductors, right? Materials such as you might have heard of, maybe bismuth telluride, and a lot of times these have certain drawbacks. So for traditional bulk thermoelectric generators, because of their inorganic nature, they could be rigid and often brittle. it's difficult to work with, often you're restricted to very small sizes. Often you have to make like lots of little modules and build them up together because of the size limitations and because of the way these materials are produced. So again, with a lot of these materials, the manufacturing process is quite complicated. There's a lot of material wastage. So, for example, material like bismuth telluride, which is one of the most common thermoelectric materials, it's very expensive because tellurium is a very rare element, and so the cost of these devices often are prohibitive, to them being actually deployed in any applications. And also, some of these materials may be toxic. So materials like bismuth, for instance, or a lot of lead-based materials, these could have toxic. They could naturally be toxic. And thermoelectric generators, they tend to suffer from low efficiencies, but the ones which are quite well established, they're much higher efficiency than the alternatives, which are organic or polymer-based thermoelectric materials. So why I'm interested in these is because if you have a polymeric or an organic thermoelectric material, you can actually make it flexible, you can make it bendable. So, for instance, this is one of my pet projects at the moment. You've got hot water pipes, especially, like I said, in a cold country like this, you've got a lot of heating works, a lot of heating pipes, and they're constantly at a temperature difference between the heating pipe and the rest of the world. So if there's a way that we could wrap these pipes using a flexible thermoelectric material, then we can make use of that temperature gradient. You cannot do that with bulk thermoelectric generators easily, but you can if you can print them and you can make them bendable. Also, we can customize the shapes, the sizes, the design. There's a lot of flexibility in the design. You can scale up to large areas. Of course, the disadvantages are compared to these traditional materials, these have much lower efficiencies. And the reason for that has to do with the material properties. So the way we compare thermoelectric materials is using a parameter known as the thermoelectric figure of merit, which is called ZT. And it depends on what's known as the Seebeck coefficient. So this is a parameter that tells you for a certain temperature gradient, this is the voltage that a material will produce. It depends on the electrical conductivity of the material, and it inversely depends on the thermal conductivity of the material. You can kind of see, if you look very carefully at those parameters, you kind of see what the problem here is. If you want to maximize ZT, you want to have as high of an electrical conductivity and as low of a thermal conductivity as possible, but you can see that most materials, well, all materials which are good electrical conductors are also likely good thermal conductors. So decoupling this is where material scientists get all excited and they try different things. So we want to sort of optimize these parameters, but they're interlinked, and that's the main issue. So if I just concentrate on the numerator for a second, then one of the advantages that polymers have is they inherently already have a low thermal conductivity, right? So when I say polymers, I mean they have to be conducting. So these conducting polymers, they're not very good electrical conductors, and they're not very good thermal conductors either. So if I keep the thermal conductivity aside for a second and just concentrate on the numerator, then I would have to think of ways by which I could increase these two parameters, the Seebeck coefficient and the electrical conductivity. And this is where combining different materials comes into picture. So the idea is that I use a polymer backbone, so I use like an organic material, and then I kind of introduce inorganic nanomaterials into this mix so that I can artificially bump up this power factor while maintaining the low conductivity. So to do this, I use a method called aerosol jet printing. This is an additive manufacturing technique where you can put down very small features over large areas. So anything that you can do by photolithography, we can do directly by aerosol jet printing. So you basically load up your nozzle, your ink holders, and I won't go into the details of how this works, but we've published many papers over the years on the exact, the way this works and how you can optimize it. But using this, you can put down different materials and build up circuits and devices very, very efficiently and very quickly. What this also allows us to do is it allows us, as I mentioned, to mix different components. So we've got our organic thermoelectric material, which gives us the low thermal conductivity, and then we've got the inorganic component, which gives us the high power factor. And we do this by sort of co-printing these two different materials at the same time. So it's almost like mixing graffiti inks. And what this allows us to do is it gives us a way of having almost ideal dispersion, because the problem is you might think, oh, well, I could just mix it all in a beaker and deposit it. But it doesn't work that way, because if you try to mix in nanoparticles, they tend to clump, they tend to agglomerate, so you don't end up with a fine dispersion. And this could actually lower your thermoelectric properties, which is what we don't want. But anyway, so we've done this, mixing, so here we've got our inorganic component, which is bismuth telluride or antimony telluride. Here's our organic component. So P.PS is a very common organic thermoelectric material, and we co-print these into various structures. So here you can see, for instance, you can see these printed thermoelectric devices which are very flexible. In this particular instance, we've also introduced multi-wall carbon nanotubes to improve the electrical conductivity. And what do we get at the end of it all? So I've got a video here to show you what we get at the other end. So here's a thermoelectric device. I don't know if you can, let me see if I can get my cursor. So here's what we call a thermoelectric mat. So in the middle, we've got like say a hot drink, and there's a temperature gradient between the hot drink and the rest of the surroundings. And this mat has thermoelectric legs which are printed. And you can see that just that temperature difference is driving this LED circuit here. What's happening now is we're putting in ice, so we're reducing that thermal gradient. And as you'll see up here, you can see that the LEDs start to fade because we're artificially reducing the temperature gradient. So we call this a thermoelectric coaster. So you have this coaster, you can put your hot tea or your cold beverage or whatever, and you can monitor whether it's at the right temperature. And all of this is self-powered. This is just a fun demonstration that we use, but it shows you how you can very, very easily convert these materials into actual working devices. So I'm conscious of the time, so I'm going to try to go a little faster. So I'm actually quite close to the end, and I would love to take questions. But just to say again, from a mechanical engineering perspective, you can see how using methods like this you can actually introduce geometrical patterns. So here we use this meandering structure, which you can print using your functional materials. And when you peel this off, you can strain this material, and this is just by virtue of this design that we've chosen. So not only can we make these thermoelectric devices flexible, we can actually make them stretchable as well. So you can see that this device goes from 0% strain all the way to 100% strain, and it retains a lot of its properties in doing so. And just the last few slides to show you some of the other things that we do. You can actually build up three-dimensional structures layer by layer using this method. So in this particular demonstration, you can't see the droplets as they exit the nozzle, but you can see the structure being built up as they collect on the substrate. So this is what this is a form of additive manufacturing which allows precision engineering and minimal wastage of materials, and it's actually quite mesmerizing to watch. So what do we do with 3D structures? Well, I'm very happy to show you this work. It actually just came out literally yesterday in Nature Materials. And what we've shown here is that you can actually use aerosol jet printing to print three-dimensional electrodes onto which you can attach biocatalysts that can be used for biophotoelectrochemistry. So biocatalysts, and these can be enzymes or living microorganisms. They can be electrochemically connected to electrodes for biotechnological applications. So in this case, what we showed is cyanobacteria, which are kind of photosynthetic bacteria. They're free-living, self-repairing, abundant. They're solar-powered biocatalysts, and they can be wired to electrodes for electricity generation, which is what is photovoltaics. And this study, we demonstrated how bioenergy from photosynthesis can be more efficiently harnessed in the future, and we provided new tools for this kind of three-dimensional electrode design. So the idea is that you put down these I lost my pointer. You put down these cyanobacteria on these electrodes, and as they interact with incoming light, they produce electricity, which can be used to drive an external circuit through some electrochemical means. Now, ordinarily, people started by putting them just onto flat electrodes, and you get a certain amount of output current in the current that you can produce. Then they went to microporous structures, so more almost like scaffolds. So you have more area of interaction between the bacteria and the electrodes. Again, improvement in the current. And this is the work that we showed. So these are aerosol jet printed electrodes. So these are indium tin oxide electrodes. They're conducting and they're transparent because you need light to be able to get into the device. So here are some images kind of showing you what these pillars look like. And by tuning the printing parameters, you can also put down some structure on the nanowire, so you can make these pillars rough as you print. And by increasing by such a large amount the area over which these bacteria can interact with the electrodes, so this is sort of almost the highest, well, not almost, this is the highest reported value of the kind of photocurrent or the biophotocurrent that these types of devices can produce. So I just wanted to put that there just to kind of give you an idea of other energy applications that can come out of additive manufacturing. So I'm actually going to, I'm just aware of the time, so I'm going to skip ahead. I had just one other thing to show you, but I think I'm going to, I'd much rather take some questions, but maybe I can just show you the video since it's here. We also use this technique to, what we're currently doing is we develop these sensors, let me see if it works, that can be used to monitor forces during hip replacement surgery, as you can see here. So this is a ball and socket joint. When the hip is replaced, essentially, all of this is taken apart and you have an artificial hip that's put into place. Currently, these experiments, these surgeries are done, it depends on your surgeon's skill. So we're trying to remove some of the ambiguity in that by introducing sensors that can guide this surgery. And I just wanted to put that there to kind of, I'm just trying to complete the cycle. So, I kind of showed you how we develop these materials, how we go to devices. I showed you some nanoscale characterization, how we really look into the properties of these materials at the nanoscale. And this is the other end, which is, this is the device that we're actually putting out, that we're trying to commercialize, that we're trying to get into the real world. So that's sort of the entire cycle. So I'm sorry I can't talk about this much, but I'd be happy to take questions. Like I said, at the start, as was introduced, we've spun out a company that is now commercializing this product. And since I've spoken about various different things, I don't have a conclusion slide, which is just a snapshot of a range of materials and devices that I've discussed. And of course, with that, just once again acknowledging my fantastic group for their hard work, and of course the funding bodies that support the work. Do check out more of our group's work on our website or by following us on Twitter. So that's it from me. Thank you for your attention. I'm sorry if I went over time, but I would really be happy to take questions at this time. So thank you very much
for the very interesting talk.
Thank you, Professor Sohini, for that very illuminating talk on engineered nanostructure polymers, both for using the wasted energy, which in the days of Internet of Things, when you have sometimes the first value devices. So if they can utilize this kind of thing, it will be valuable. Same thing with biomedical. Now there are a few questions.
Okay.
Professor Dhiral Patil, you want to ask the question yourselves?
Sir, go ahead, sir.
Okay. Professor Dhiral Patil has a question. Are there mechanical thermal property tests on nanostructure, for instance, the piezoelectric materials you mentioned, specifically to establish deterioration factor? That is, today you have a piezoelectric material.
Yeah.
Then what will happen after 1 year, 6 months, etc.? This deterioration.
Yeah.
So that continuous use of these functional materials.
Yeah.
etc.
Yeah. Thank you. That is an excellent question, and believe me, it's one that we think about a lot. Because when these fields were first introduced, so obviously, you can do a lot of fantastic material science and come up with devices that, that have seemingly high performance, but you're absolutely right. Like, how long does that performance last for? And what we found at the start was that, there weren't very many reports about this sort of fatigue performance or this long life performance. And this is something we're very interested in. So we started looking into this, and this is where we found that, for instance, with piezoelectric materials, if you're working with ceramics or with inorganic materials, or zinc oxide is a very common material that people use because it's so easy to produce. There are two things that happen. One is, over repeated stress and strain cycles, these materials break apart. Or in the case of materials like zinc oxide, they are affected by the environment. So humidity, temperature, just even exposure to light is enough to degrade them. So a lot of the initial devices, I don't think would have lasted more than a few weeks. However, This is one of the reasons why we moved to polymers, because inherently these have much better mechanical stability. So we test all our devices over multiple, we fatigue test them. So, the setup that I was showing you, that shaker setup, we leave this running for days to see, how does the performance change? And yes, invariably over time, there might be slight dips in performance, but then they tend to stabilize, particularly with these polymers. And if they're embedded in that template, then they're protected from the environment. So we've actually shown zinc oxide within templates where they're completely impervious to any environmental change. So we have devices from 3 years, from 4 years ago, which still work, which is great. And I think we are quite proud to actually show this data. We make sure that whenever we put out a paper on energy harvesting, we show fatigue data. So I think that is one of the things, the material itself, working when you're working with polymers that improves your longevity, but also the device structure itself can be quite protective. When it comes to triboelectric materials, this problem is even worse because it's a surface effect. And so you can imagine you're rubbing, and over time you will wear the surface down. And as you wear the surface down, the performance will dip because it's the amount of charge that you're developing across the surface. So one of the common methods to increase performance used to be, and it still is, to structure the surface. So instead of having a plain surface, have a nanostructured or microstructured surface to increase the surface area. But then as you have repeated rubbing cycles, over time, you will wear that down and it's all gone. So the way we counteract this is by working with materials that have an inherent surface charge density. And these are ferroelectric materials. So this is where I showed you the spontaneous polarization. So certain materials, they have a spontaneous polarization. It doesn't matter what the state of their surface is. They have already a spontaneous polarization. So we focus on that. Because like I said, you can wear the surface down, but the material itself is able to have this surface charge present, and that gives it the longevity. So all our triboelectric devices as well have been tested over months, if not years, and we do what is called accelerated testing. So we do high frequency testing. So we over a period of a week, we try to put in as many cycles to see how far this material will survive. So I hope that answers your question. It's a very relevant problem, particularly in industry, because I've been talking about trying to replace batteries, but I need to make sure that my devices can outperform.
Thank you.
So, yeah.
Thank you, Sohini.
That is a very excellent thing. But then I think the next question is relevant to what you just now said. What Sheena Sheikh asks is this piezoelectric versus triboelectric.
Yeah.
In terms of things, which in general is more efficient for people because of what you said.
Yeah. Again, this one's a tricky one to answer because when you say a piezoelectric device or a triboelectric device, it's hard to compare like for like because there are a range of different materials that you can use for either. Having said that, I would say in general, at least with the range of materials that we work with, triboelectric devices tend to produce higher energy outputs, and that has more to do with the way the mechanical energy couples to the device. Because in a piezoelectric material, remember, you have to physically strain the material to get an output. With a triboelectric material, you don't have to strain the material. You just need to be able to make some sort of contact with the surface. So in a sense, the mechanical coupling is almost more efficient in a triboelectric device. And that's why I think that they tend to have higher efficiencies. However, for sensors where you want to make a force sensor, say, or something that's sensitive to pressure, I would say a piezoelectric material, hands down. And these are already used in lots and lots of sensing applications because of that property. So they're remarkably important technological materials. You find them in ultrasound machines and in microphones, in your gas lighters, and there's a reason for that. These are materials we've known for a very long time. But I think in terms of microscale energy harvesting, I would probably rate triboelectric slightly higher. But yeah, I mean, it really depends on the material system that you're using.
But then she also asks, for instance, cellulose is a natural piezoelectric polymer.
Yeah.
What do you think of it for this?
Yeah. So cellulose was one which we were very interested in because it's natural, because it's so abundant, right? It's one of the most abundant biopolymers out there. So here's the thing, yes, so we've got, cellulose in trees, in everywhere. So can we just attach some wires and hope that we harvest some energy? The answer is it's not quite as simple as that. And the reason for this is that individual cellulose nanocrystals will have some piezoelectric properties. Again, this is just because of the structure of the cellulose. But when you have a whole bunch of them, if they are not aligned, it doesn't matter, because each individual dipole will cancel out with the next. So overall, unless you have some overall alignment that you force into these materials, you will have no net piezoelectric effect, even though the unit itself is piezoelectric. It's like with PVDF. If you have alpha phase PVDF, you're not going to get anything out of this, even though in principle it's supposed to be a piezoelectric polymer. So cellulose and other biopolymers have the similar problem. So it's not like you can just attach a bunch of electrodes to a leaf and hope that it works. No, you have to engineer the material in that leaf. So you have to have some sort of an artificial leaf, which maybe still is based on cellulose, but you have to come up with ways by which we can align the cellulose so that you can first of all get the maximum amount of strain in a particular direction, which will then produce electricity. So I hope that answers the question. But it's a great starting point. But yeah, there is some materials processing that you will require before it will do the job.
All right. Thank you so much. I think we have partly answered her question. Now, Saraswati Kulkarni asks, I think it is the PVDF you just know, some of the material you mentioned. Now the thing is, due to humidity, do you expect any effect? Yeah, absolutely. In fact, humidity is a bigger problem for nylon because those are really, really hygroscopic. And in fact, this is why nylons used to be studied in the 80s, 90s, but then for piezoelectric properties, and then they weren't pursued because it was a known effect that moisture or humidity would affect their performance. So I would say, again, most of the devices that we work with, you will notice are encapsulated. So they're either, the nanowires themselves are either embedded in the templates, which means that the effect of humidity is minimized, or there are ways by which, if you don't have that system, you can still encapsulate the device in such a way that the effect of humidity can be minimized. But you're absolutely right, humidity is a factor, and there are studies that have shown how, depending on the day that you measure, you might end up with something different. So some of these actually are quite difficult to reproduce. People try it in a different lab and they don't get it, but that's because they're doing it under different conditions. So absolutely, these are definitely questions worth thinking about when designing the device. So that's the materials part, and this is where the device engineering comes in. Like, how do I build the device around it to counter these problems? Okay, thank you. Now, Nupur Saxena has a question.
Yeah.
Now, can you make a composite material having low thermal conductivity and high electrical conductivity, so that what you earlier talked about the power factor, you can improve it?
Yes, absolutely. In fact, that is what we were trying to do. So the reason we decided to combine the organic and the inorganic is because the organic already has a naturally low thermal conductivities, without having to try very much. Whereas, if you take an inorganic semiconductor, these will typically have a much higher thermal conductivity. So we use the organic conductor for its low thermal conductivity mostly, but its electrical conductivity is quite poor. So this is why we then embed our nanomaterials, which are the inorganics, which have higher electrical conductivity, which have higher Seebeck coefficients, and we try to combine these two. So the studies that we've done we've done these studies where we very systematically varied the amount of nanoparticles that you put in, because if you go over a certain amount, so there's an optimal range. If it's too low, then you probably don't have high enough electrical conductivity. If you go too high, you might end up with a very high thermal conductivity because you have too much inorganic material there. So it's trying to find the sort of, it's usually not the middle, but try to find the optimal range. So absolutely, this is exactly what we are trying to do. There are other ways of achieving this, mind you. So this is not the only way. But we quite like this because we have good control, because we're printing both of these at the same time. So we have good control on printing the composition, and we have good control on the dispersion. So that is important. So when you do composite engineering, you will see that the dispersion, especially of nanomaterials, is a big problem because they tend to, like I said, they clump up and then they're no use.
Okay. Thank you. Now, Professor Kirti has a question.
Yeah.
You mentioned about using functional material for the microfluidic applications. Now, could you please describe the methods used to actually change the channels for geometry?
Yes. Thank you. Sorry, I didn't get to talk very much about the microfluidics because I was trying to concentrate more on the energy application, but I'm glad you asked. So the way most of these channels are made is they are made from a mold, right? So you start with some kind of a mold, and then you pour your some sort of a silicone or some material over it, and then when you strip it apart, you have your channel in there, right? And then this is the microfluidic channel that you use. So what we do is when we print this mold, so we do not use standard techniques like lithography or laser print, cutting, etc. We literally print these molds with our aerosol jet printer or even with a 3D print, some other 3D printing depending on the size that you want. But what we then do is we put down a functional material. So let's say, for instance, you want to make a device where one part of it is hydrophilic and the rest of it is not, or one part is hydrophobic and the rest of it isn't. So just that section of the mold, we would put a hydrophobic material on the mold, so that when you then cover it with your PDMS is a very common material that people use. It could be any other silicone. And you peel it off, it takes that functional material with it. So we have a paper where we demonstrated that by doing this, you can make selectively some parts of your device hydrophobic and other parts hydrophilic, and this can control the flow. The other thing that we can do is we can directly print our circuits onto the microfluidic channel base. Now this, and I think someone asked me how the I think there was a question that I spotted, like how does the force, the microfluidic force sensor work, the one that I showed at the very end that we use for hip surgeries, or that we intend to use for hip surgeries. So then what we've done is we have a microfluidic channel. So imagine this is a very tiny channel through which we can have liquid moving in and out. What we've done is we functionalize this channel by introducing a set of capacitive electrodes within that channel itself. Now, the capacitance of the capacitance that these electrodes are measuring are affected by the dielectric properties of that channel. So imagine you've got, this channel is connected to a reservoir, and you apply a force to this reservoir, it pushes the liquid up the channel. The higher the force you push, the further up the channel it will go. And we've got these electrodes which are embedded, which senses this, right? Because, we've got electrodes across the entire channel. So this is how we know just by measuring the capacitance, how far that liquid has moved. So we've calibrated this force with respect to how far so the harder you push, the further the liquid goes, the higher the change in capacitance. So that's how we functionalize. So this is how we made a force sensor. Why is this? There are other ways you could make force sensors, right? So why a microfluidic channel? For a very good reason. And that is because if you look at the hip joint, it's a very tight joint, right? There's hardly any space to get anything in there. So a conventional sensor would just not be able to fit. So we use microfluidics because one, we can make them very thin and very conformable. Actually, maybe I can show you since you asked. If I just share my screen, so we can make them very thin and very conformable. Hang on just a second. So this is typically what one of these sensors would look like, and the blue thing that you see there is basically the fluid that moves up and down. And the other thing we can do is we can change the material of the channel of the microfluidic device, so that you might need to push harder to get the liquid to move. And this is important because the kind of forces that you get in hip joints, so typically hundreds of newtons, maybe even thousands of newtons, well, not 1,000, but up to a kilonewton or so. And if you have a very thin sensor, these typically cannot measure these high forces. But this particular device can, because essentially we use the microfluidic, the channel material to shield the forces, so that we can tailor it. So if I play that video again, one is that it fits into that tight device because it's very thin, it's very conformable, but also this large force that's coming in from the femoral head. So this is from the thigh, the part of the implant, the thigh implant. We can measure because of the way we engineer the material in that channel. So I hope that's clear.
Okay, now I think we may have to very soon end, but some 2 questions we will ask.
Yeah.
The others probably will have to write, I think. One is from Professor Dheeraj Patil. See, this bioprinting, you mentioned towards the end of your thing, something very nice. The question is that bioprinting, along with this use of nanomaterials on fabrics, can you use it to lock or disinfect, say, bacteria or viruses on the surface?
Yeah, so it's something that we have thought about. So, for instance, we've actually done some experiments with we're trying to look at fungi actually. So for instance, these don't like being anywhere near silver. So we were testing various various different materials that we could print down in specific areas that could be used to counteract the effects of biofilm formation. So maybe prevent biofilm formation altogether by modifying the substrate itself. So we have some preliminary work in this area, but yeah, these printing methods are excellent because yes, you have the final product, but then when you're trying to go through a library of materials to find which materials are maybe antimicrobial or anti-biofilm, etc. You can quickly do these experiments over a large range of materials, and this is exactly what we're trying to do. So we put down all these different materials, and then we flow. In this case, we were trying to introduce fungal populations to see where they would grow and where they wouldn't, and then that would reduce our that would reduce the number of materials that we'd be interested in. So yes, I would say in terms of screening materials for these kind of applications, these techniques are amazing because it's very easy to go from an ink formulation to a printed device using these types of techniques. I hope that answers your question.
Now, one question on me I want
Thank
to
you,
ask.
Sohini.
This nanomaterials, engineered nanomaterials, once they become widely used, some will say the plastic 1907 invention, 1950s, etc., people widely used. Now we know. Is there a possibility of toxicity like that? What do you feel?
Sorry, is there a possibility of?
The same kind of toxicity, and see once you have wide scale use of engineered nanomaterials, that you go into the environment or even a human body when you are using it for biomedical.
Yeah.
Then
these are very, very relevant questions, and I'm glad you're asking this, and everyone should be asking themselves this question when working with any kind of nanomaterial. So nanotoxicity obviously is a big issue. One of the ways we try to circumvent this is this is why I'm very interested in biocompatible. I keep saying biocompatible polymers. But one of the reasons is that these are. If I'm working with materials like polylactic acid, I know that the body is able to absorb and get rid of this in a safe way, or materials like cellulose, etc. So one way is to to focus on biopolymers, but also from a kind of wider environmental perspective. You do any new material that you come up with in this day and age, I think you really need to think about the cycle, the life cycle. Like how is this material going to, at the end of its lifetime, where is this material going to end up? Is it going to be released into the environment, particularly if it's a nanomaterial? What effect this will have on human health, on the environment? So these are all excellent issues, and I know that in the synthetic polymer world, these are things that people are constantly thinking about. So our way of doing things at the moment is trying to focus on non-toxic. Again, this is why we don't use lead, for instance. We try to avoid those materials that we know we probably shouldn't be touching at this stage. But those that do, it's not to say that all no one should touch these materials, but people should be thinking about what the life cycle of the product is. So it's a great question, and like I said, in my group we try to focus on biomaterials or biopolymers, and we try to functionalize them when they're not, when we know that they are capable of doing more. We use materials processing to enhance their properties.
Thank you so much, Professor Sohini, for an excellent, insightful talk, and for the audience, for the penetrating questions, for participating. I think we will have to stop. No?
Yeah, thank you very much for having me.
The last hour was truly engaging and insightful. It's time to express the gratitude to all those who have made this wonderful event possible. Foremost, I thank Professor Sohini Kar-Narayan for sparing her valuable time and for enlightening talk on functional nanomaterials and devices for energy sensing applications. A thanks to the contributors of the GCOE-ACE organization for executing this and many more lectures as a part of TREES. We thank the administration and professors of IIT Dharwad for supporting this event. And lastly, I thank the wonderful audience for your presence and eagerness to learn and that motivates us all. With this, let's conclude the event. Thank you, everyone. Have a great day. Have a great Women's Day.